Okay, this is day 1 of Unit 9. So we started with this warm-up problem today, just a real simple problem on probability. Um, and I did mention to students that if you don't know uh, the makeup of cards, you probably need to know that, because we'll often look at probabilities of cards in this unit. So you should know the basic makeup of cards, like how many cards are in a deck, how many clubs are in a deck, jacks, queens, kings, how many face cards, how many red cards, how many black cards, how many clubs, spades, hearts, or diamonds. You should know all of those. So this one, how many clubs are there? Well, there are 13 clubs out of a total of 52. That simplifies to 1/4. So the probability of a club is 1/4. And unless you're told otherwise, you should usually use fractions, simplified fractions for probabilities. So then we talked about, we took some notes in class on odds. So we just did probability, and we know that for probability, probability is defined as the number of times an event occurs divided by the total number of events. Total number of events. So odds is also defined as the number of times the event occurs in the numerator, but the denominator is what makes odds different than probability. The denominator is the number of times the event does not occur. Now, with probability, we know probability can equal, probability can equal 1 or be less than 1. It can be equal to 0 or be greater than 0. So it's a number between 0 and 1 or equal to 0 or 1. With odds, that's not the case. Odds, you have to have two numbers. So it's a comparison of two numbers. So if you're calculating odds and you come up with something like, let's just say example for odds would be like 4/4. Well, for that, you want to simplify 4/4. But you don't want to just say that 4/4 equals 1. That doesn't make sense for odds because we always need to have two numbers to compare. So 1/1 is fine, or 1:1, or 1:1. But you need the two numbers to compare. Again, you want to simplify if you can, so don't leave it as 4/4, but don't simplify it to 1. On the other hand, if I'm calculating probability and let me just have an example. Let's use the same two numbers, 4/4. There, with probability, I can say that 4/4 equals 1. Okay, so it's possible to have a probability of 1, just one number, but not for odds. Odds, you need two numbers. So let's put these in your notes. So finding the odds of selecting a club, well, the odds, number of times the event occurs. So we already said there's 13 clubs. And then the number of times it doesn't occur, well, that means all the non-clubs. Well, there's 52 cards total. Subtract 13 gives me 39 non-clubs. So 13/39 simplifies to 1/3. So that's the odds. B, find the odds of selecting a face card. Well, face cards are jacks, queens, and kings. Aces don't have faces, and jokers are not part of a standard deck. So there are 12 face cards, and there are 52 total cards, so that means there's 40 that are non-face cards. So I simplify that. 12/40 simplifies to, what, 4 goes into each of those, so 3/10. 3/10 is the odds for selecting a face card. Okay, so then we did these, so you want to add these to your notes as well. So if the odds in favor of an event occurring are 3/5, find the probability of the event occurring. Well, keep in mind that the numerator of both odds and probability, they're the same. So I keep the 3. Now I just have to figure out what to do to get the denominator. I want the probability, which has a total in the denominator, and I have the denominator of odds, which is the number of times that it doesn't occur, whatever this event is. So if I want the total, I'm going to take the number of times that occurs, 3, plus the number of times it doesn't occur, 5, to get the total, which is 8. And that's my probability. Okay, so then example 2b is kind of the opposite here. This time I'm giving you the probability, which involves the total and the number of times it occurs. And I want the odds, which is the number of times it occurs and the number of times it doesn't. So 4 stays the numerator, and then I want the number of times it doesn't occur. So 7 minus 4 is 3. 4/3 is are the odds when the probability is 4/7. So then we did take some time in class to work on page 4 of the new packet. We skipped problems 8 and 9 for now. We'll come back and do those later, but we did complete all of page 4. And then after that, I did go over the answers. So make sure that you, if you weren't in class today, that you do all the problems on page 4 and check your answers with someone who was in class, or check your answers with me. Okay, then we moved on to page 3. This Rochambeau problem is on page 3 in your packet. So take a look at that. So with Rochambeau, that's kind of the French version of rock, paper, scissors. And basically, it's very similar to our rock, paper, scissors, except for that there are 3 players rather than 2. And what you're doing is you're all doing, deciding whether you want rock, paper, scissors. If all 3 players match, so in other words, like they all have rock, they all pick rock, then player A gets a point. And if 2 of the 3 players match, so like rock, and paper, then player B gets a point. And if none of the players match, so I have 1 rock, 1 paper, 1 scissor, then C gets a point. So that's how you play the game. And so what I first just asked was, there's a question there on the bottom of page 3 that says, who would you choose to be if you could? Hopefully you're realizing before we've even done any math, it seems to me that 2 out of the 3 matching is going to happen the most often, okay, because it's harder to get all different or all the same. So if you could choose, you probably want to choose player B, because it seems like that would occur the most often. And again, we haven't even done any math yet, but that's just kind of using some common sense. Okay, so then we talked about in class how there's 2 different types of probabilities. There's what we call theoretical probability and what we call experimental probability. We're going to first make a tree diagram to represent this game, and we're going to look at the theoretical probabilities. Then later, tomorrow, we'll play the game, and we'll record the results. And when we record the results, we'll calculate the experimental probabilities using those results that we record. Okay, so experimental, you have to conduct some sort of experiment and keep track of data and count, versus theoretical is probabilities that are based on logic, or just common sense. So if I'm flipping a coin and I'm just calculating probability, theoretical probability, the probability of heads is going to be 1/2. But if I'm conducting the same experiment with coins, but calculating experimental probabilities, I'm going to keep track of how many times I get heads, how many times I get tails, and then I'll use those numbers, that data, in order to calculate the experimental probabilities. So that's the difference between the 2. Again, we only had time today for theoretical probabilities. So, and we talked about those using a tree diagram. So that's what we're going to talk about now. So we're going to make a tree diagram here. And what I said in class is you always want to, before you make a tree diagram, start by asking yourself 2 questions. The first question is, what are the events? Now, the events are always what is taking place in the problem that the people in the problem have no control over. So in this problem, we're told that there are players A, B, and C, and we don't have any control over that. That's part of the game. Those are the events that are occurring. So A, B, and C players. A lot of times you can easily identify the events by the word and. The events usually are separated with and. So and is your keyword. And once you've figured out what the events are, they become the layers of the tree. And I'll explain more what that means in a moment. The second question is, what are the choices? So every problem I said you're going to have definites, things that you don't have control over, and then every problem there's going to be something where the player or whatever the whatever we're talking about, has choices. The choices, in this case, when we're talking about the player A as being the first definite or the first event, well, player A has a choice of either rock or paper or scissors. So rock or paper or scissors, those are the choices. Choices, you'll notice, often use the word or to separate them. The choices are the branches of the tree. Okay, so I'm going to make my diagram here on the next slide, but I know that I'm going to start off with the first event, which is player A. And player A has choices of rock or paper or scissors. So if I think about it, that tells me that I'm going to start with 3 branches in the first layer, and the first layer is representing player A. So let's go ahead and make a diagram that reflects that. Whoops. So we go. So I'm going to, and you can either do tree diagrams from top to bottom or from left to right. Personally, I think it's easiest to keep them spread out if you go from top to bottom. So that's what I'm going to do here. So you're going to do this on page 3 in that big space that's on page 3. We're going to make ourselves a tree diagram. This first layer is representing player A. Player A has choices of either rock or paper or scissors, and I'm putting those on the branches. So the layer is the player A, that's the definite. The choices are the branches, rock or paper or scissors. Now, the next layer is going to be layer B, player B for layer B. And player B can either choose rock or paper or scissors. So I'm going to, again, mark rock, paper, scissors for player B. So I'm going to do that again. And I'm going to do that one more time. Okay. So then off of my second layer, I'm going to make my third layer, which would be the third player, which is C. And I know, once again, rock, paper, scissors. Rock, paper, scissors. Rock, paper, scissors. And one last set of branches, rock, paper, and scissors. Okay, so there's our diagram. Now, with each one of these rocks, so I'll just start here with this rock, the probability of player A choosing rock is, hopefully you realize, 1/3. Same thing with player B, and same thing with player C. So if I'm trying to figure out the probability of rock, 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 I would take those 3 probabilities, 1/3, and I would multiply them times 1/3 times another 1/3, which would give me 1/27. So each of these ending probabilities here is going to be 1/27. By the way, this, if I were to write all of these out, the next one, rock, rock, paper. Rock, rock, paper. Well, again, we said that's 1/27. If I were to write every single one of these possibilities out, rock, 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 paper, rock, rock, scissors, rock, paper, scissors, rock, paper, rock, rock, paper, scissors. If I wrote each one of those options out, that is called the sample space. A sample space is a list of all possible options or outcomes. Okay, so I'm not going to take the time to write out the sample space, but what I am going to do, I'm going to answer the question on the bottom of the page, or towards the bottom of page 3, is what's the probability of A winning, the probability of B winning, and the probability of C winning. Okay. Now, we know that they're each going to be out of 27 because there's 27 possible outcomes in the sample space. So we know they're out of 27. We're going to start with A. Now, if you recall from the explanation of the game, A wins if all three match. So rock, 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 paper, 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 scissors, scissors, scissors. So that's only happening 3 times, right? We have rock, 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 paper, 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 and scissors, scissors, scissors. So that means A is going to win 3 times out of 27 total times. Now, I realize that's going to be simplified, but we're going to leave it as 3 27s for a minute. Now, B is going to be the one we already said that occurs the most often. So we're going to skip that for a moment and we're going to move on to C. So C occurs, remember, if they're all different. So if they're all different, I'm going to go through my sample space here by looking at the tree diagram, and I'm going to figure out all the times where they're all different, and I'm going to count those. So rock, rock, I already can't count this whole section here because it's rock, rock, and I don't want repeating. So I'm going to move on to the rock, paper. Well, rock, paper, scissors would be all different. So that's 1. So I'm just keeping track here, counting on my fingers. So rock, paper, scissors, that's 1. Then I have rock, scissors, paper. That's the only one in this section that I'm going to count. So that makes 2. Now I'm moving over here. Paper, rock, scissors, they're all different. That makes 3. Paper, paper, that won't work. So paper, scissors, rock, that will. So that's another 1. So that's 4 so far. Now we're moving over to this section. Scissor, rock, paper, they're all different. That makes 5. And scissor, paper, rock, that makes 6. I can't do scissor, scissor because then I have repeating scissors. So I have 6 total. Whoops, not for B. We're on C. 6 total times out of the 27. So now hopefully you realize that one way to get B, probability of B winning, would be to go through and count all of the times where 2 are the same and 1 is different. That's the long way to do it, though. It would take us a while to go through this whole entire sample space and count. So the quicker way, hopefully you realize, is if I have the probability of A winning, and I have the probability of C winning, and I want the probability of B winning, well, the probability of B winning is just all the rest of the times that C or A don't win. So I'm just going to add the 3 and the 6 and get 9 and subtract that from 27, which gives me 18. That means B is going to win 18 out of the 27 times. Okay, now that we have those 3 probabilities, 3 27s, 18 27s, and 6 27s, now we'll go ahead and simplify them. So we have 1/9, 2 thirds, and here 2/9. Okay, so now we have those probabilities. Okay, now that's really all we did with this problem today, was just talk about how to set up a tree diagram, make the tree diagram, and then find the theoretical probabilities. Remember, these 3 are all theoretical probabilities based on logic or our tree diagram rather than experimental probability. Tomorrow we'll start class by actually playing the game and collecting the experimental data, and then we'll compare those probabilities with what we have here to see if they're similar. And then we'll also answer that question on the very bottom of the page, which says, how do we make the game more fair? So we'll talk about that tomorrow. That takes care of today's lesson. Your homework is worksheet 1 and all of it, and worksheet 3, just problems 1 to 14. Please do those for tomorrow.